This is section 1.3, Properties of Graphs of Functions. By the end of this lesson, I can state the intervals over which a function is increasing or decreasing, discuss the symmetry of a function and determine if the function is odd, even, or in fact neither, determine if a function is continuous or discontinuous, determine end behaviors of functions, compare and contrast the properties of parent functions, and sketch a function based on given properties. Certain properties of functions, such as domain, range, and intercepts, have already been covered so far. In this section, we will be examining other properties of functions. So the first other property of function that we are going to examine is intervals of increase and decrease. An interval of increase is a set of x values over which the value of the function, so the y values or the f of x values, increase. Put differently, the function is going uphill as we move left to right along the x values. This means that the function has a positive slope. So if we look at the diagram right here, we can see an interval of increase right here. As we go from left to right, the function increases. An interval of decrease is a set of x values over which the function decreases. The function is going downhill, right there, as we move left to right along the x values. And the function will have a negative slope for these values, right there. That would be a line with a negative slope. For the graph below, indicate using interval notation the intervals of increase and decrease. So if I were to look at interval notation here, I need to identify the parts of the graph that have intervals of increase. And if we look very closely, we can see that the graph continues on forever towards negative infinity, and it increases until we get to x is equal to -3. And at that point, we stop. So the first interval of increase there goes from negative infinity to -3. And note that it does not include -3. And that's because at the point -3, it actually switches from being increasing to decreasing. So at the point it makes the switch, so from anywhere from negative infinity to just before that point, it increases. We also see over here, when x is equal to 2, all the way to positive infinity, we also have another interval of increase. So what I'll write here is, so from 2 to positive infinity. That is your other interval of increase. When we look at the interval of decrease, that's when we have a negative slope, as identified over here. So from x is equal to -3 to x is equal to positive 2, we have an interval of decrease. So -3 to positive 2, we have an interval of decrease. Note well here, if a function only increases or decreases over the domain over all the x values, then we say it is strictly increasing or strictly decreasing. So if a function only continues to increase, we say it is strictly increasing, like the exponential function. If a function only decreases for the entirety of its domain, then we say it is strictly decreasing. So for example, this is an equation of a line, but it's the equation of a line that is pointed downwards. That is, it goes down from the third quadrant to the, from the second quadrant to the fourth quadrant. So if I was to just quickly sketch that for you, I would have here, and this would be, for example, a strictly decreasing function, right? Because it continues to decrease over the entirety of its domain. All right, so let's see. We have talked about intervals of functions over which the function is increasing or decreasing. Let's now look at discussing symmetry. A function is considered an even function if it is symmetric about the y-axis. That is, if they map onto themselves with a reflection in the, let's just quickly change that, in the y-axis. So as we can see here, this is considered an even function because it has symmetry along the y-axis. All right, and algebraically, we can determine that by saying f at negative x is equal to f of x. So this is the algebraic way of determining if a function is even. If a function is odd, that means that it maps onto itself when it rotates 180 degrees from the origin, right? And we can see that by picking a point over here. So I'm just going to pick this point over here. And if I rotate that 180 degrees, it maps onto itself right there. Similarly, you could also have rotated this clockwise and it would have done the exact same thing. Okay, so 180 degrees rotation around the origin and it maps onto itself, that's an odd function. And this is what we use to determine algebraically if the function is odd. F at negative x is equal to negative f at x. Okay, so we've discussed symmetry and determining if it's odd or even. Now, if it is neither even nor odd, we just say that it is neither. So if it doesn't have symmetry in the y-axis, or it cannot rotate around the origin 180 degrees to map onto itself, and therefore it's not odd, we say it is neither. So the next learning expectation was to determine if a function is continuous or discontinuous. So let's talk about continuity. A function is continuous if it can be drawn over its entire domain without any jumps or gaps or holes. A function is discontinuous if there is a break in the domain. So if there's some sort of restriction on an x value, such as x can't be equal to 0 or x can't be equal to pi over 2 radians, then we say that it is discontinuous. Here is an example of discontinuity. A vertical asymptote is an example of discontinuity. So let's take a look at these three examples that are provided for you in your notes. This first example we would say is continuous because there is no break in its domain. So we write continuous. If we look over here, we would say that this function right here is discontinuous because even though there are not necessarily any holes in the graph, we notice that there is likely, there is a vertical asymptote, and I apologize, that should be a straight line, at this value here. Okay, and because there is an asymptote, that would mean that the graph is in fact discontinuous. It breaks at this x value because x cannot be equal to that value. Finally, looking at this function right here, it certainly is discontinuous because we have a hole in the graph, which is to say this is a value that x cannot be. Okay, so a restriction on an x value, and that produces a hole in the graph. So I'm just going to label that for you right there. That is what we would say a hole, which is basically a restriction on an x value. And so therefore, this right here is now considered to be a discontinuous function. Going back to our learning expectations, we have now talked about discontinuity and continuity. Excuse me. Let's look at end behaviors now. End behavior describes the behavior of function, the y values or the f at x values, as the x values get very large, so as they approach infinity, or very small. Describe the end behavior of the following functions. It may be helpful to sketch a graph. So what I'm going to do is I'm just going to zoom in here a little bit on the first one that we have. Okay, so in this case we have an exponential function. F of x is equal to 2x. And you may recall that this function will look like this. It'll increase, and then it will go up like that. and there is a horizontal asymptote at y is equal to 0. So that means that as this graph goes towards negative infinity, it approaches 0 but never achieves 0. So that is one type of end behavior, and let's write that. As x approaches negative infinity, so as the x values get increasingly smaller, the y values, or f at x will approach 0. So it never achieves 0, but it approaches 0. The next set of, or the next end behavior is looking at the positive end behavior. So as x approaches positive infinity, f at x approaches, well, let's take a look. What does the function do as it gets larger and larger? Well, the function will go to positive infinity. And again, this is a strictly increasing function because as we go left to right, it continues to increase. The next one I'd like to take a look at is the sine function. Okay, let me just quickly zoom in a little bit more. If we were to draw the sine function, recall that the sine function looks something like this. It is effectively a wave, right? And in fact, it only goes up to 1 and down to -1. So for the purposes of this right here, we're going to ignore the x and y numbers on the graph here. And so I'm just going to sketch it for you just in a way that is a little easier to see. Okay, so I'm just ignoring my x and y values on the graph because they're incorrect with respect to this graph. So if I looked at as x approaches positive infinity, or rather as x approaches negative infinity, does the function go towards a single number? Well, it actually doesn't. There is no number that, there's no end behavior or no number that this graph basically converges on, because it just continues to go up and down. So as x approaches negative infinity, there is no end behavior. Same thing can be said for as x approaches positive infinity. Because the graph continues to go up and down in a periodic way. The next graph that we're going to take a look at is the square root function. And we say that the square root function is effectively one-sided. And that's because it looks like this. So go 1, 1, 2, or rather 4, 2, 1, 2, 3, 4, 2. And then I believe this is 9 right here, 9, 3. Okay, so if I was to sketch this, it looks something like this. Okay, that's my square root function. It's got a curve to it. And so what I would say is that this end behavior is one-sided because the graph does not exist for negative numbers, right? Because taking the square root of a negative number would yield a complex or imaginary number, and this graph is for just real numbers. So this graph does not include complex or imaginary numbers. So the only end behavior we are going to take a look at is x going to positive infinity. So as x approaches positive infinity, f at x, well, it continues to increase, so it also approaches positive infinity. All right. We've now looked at the examples of end behaviors. So if I go back to my learning expectations here, I have determined the end behavior of functions. Okay, the next thing that we have to do is compare and contrast properties of parent functions. All right. And we can do that in the end over here where we compare and contrast, but it looks like we've got some other examples to do, so I apologize for jumping around a little bit here. But it says determine whether the following functions are odd, even, or neither. Okay, so the first thing that we're going to do is we're going to check to see if it's even. So I'm going to zoom in on the first example, and I'm going to look to see if it is even, right? And if it is even, okay, let's just recall right here that if it is even, that means that f at negative x is equal to f at x. That's the algebraic definition of an even function. So that means it has symmetry in the y-axis. So what I'll do is I will evaluate this f at negative x. So f at negative x is equal to, and instead of writing x, I'm going to write negative x cubed minus negative x. And that would yield, well, back to negative x cubed plus x. So let's compare this value right here. So this is f at negative x is equal to negative x cubed plus x. Is that equal to the original function? No, it's not, because the original function had x cubed, and this has negative x cubed. Also, it had negative x, and this is positive x. So therefore, f at negative x does not equal f at x, so the function is not even. So f at x is not even. Let's take a look to see, though, if the function is odd. The function is odd if f at negative x is just equal to the negative f at x. All right. So what I'm going to do now is I'm going to look at, I'll restate what f at negative x was, because we already figured that out. F at negative x is equal to negative x cubed plus x. Now what I'm going to do is I'm going to find out what negative f at x is. Well, negative f at x is negative x cubed minus x, right? So the negative f at x right there. Okay. Let's distribute this negative sign right here into the bracket. And what I should end up with there is negative x cubed plus x. And as we can see here, negative f at x is equal to f at negative x. So since f at negative x is equal to negative f at x is odd. Okay, so we have determined, and I'll just scroll down here a little bit. Apologies for that. We have determined that f at x is an odd function. Let's go back and look at the next example in our notes. Again here, we're going to try and see if this is an odd or even function. So what I'll do is I will look at f at negative x. So that is equal to negative x squared plus 7 times negative x to the power of 4. Well, negative x squared is just equal to x squared, and 7 negative x to the power of 4 is just equal to x to the power of 4. All right, so f at negative x is equal to this expression right here, which matches the expression for f at x. So since f at negative x is equal to f at x is even. Okay, we classify it as an even function. Let's move on. For this example, I'm going to move a little quicker at arriving whether it is odd, even, or neither. So the first step that I have to do is I have to evaluate at f of negative x to see if it is odd or even. So 1 minus 5 to the negative x cubed plus negative x to the power of 7. Well, that is equal to 1 plus 5x cubed minus x to the power of 7. However, we can see immediately that f of negative x is not equal to f of x, so that is not equal to f of x, so it cannot be even. And it is also not equal to negative f at x, so it cannot be odd. So we say that f of x is neither odd or even. What we have shown is we've effectively shown how to algebraically determine whether a function is odd or even. You can actually just, however, take a look at it graphically. Remember, if it is even, it will reflect upon itself in the y-axis. Well, we know immediately that it is not even because there is no reflection in the y-axis for f of x is equal to sine x. However, if you can rotate a point 180 degrees and it arrives at another point on the graph, then it is definitely odd. And we can see that is the case right here. If we rotate these points 180 degrees, we map onto the function. So f of x equals to sine x here is an odd function. So we can actually just take a look at the graph and determine if it is odd or even. All right? Let's move to the final example, which is the cos graph. Looking at the cos graph right here, we can see that it is reflected in the y-axis, right? So it can map onto itself directly in the y-axis. So therefore, f of x is equal to cos x is an even function. Okay. A couple more examples on continuity. We can look at determining whether a function is continuous or discontinuous. So let's just take a look at this entire example here. So example 4 asks us to determine whether the following functions are continuous or discontinuous for all of the x element of real numbers. So we can think about this right here. If we look at this expression right here, are there any values that x cannot be? Well, no, there are no values or no restrictions on x. So let's write that. So no restrictions on x. And finally, if we actually took a look at this graph, this is just simply a quadratic, right? So it is a parabola. I apologize for my accuracy there. But if we look at it, that's just a parabola, and there are no restrictions on any of the x values. If we took a look at this example, though, you will see that there are restrictions on x, right? Because of the square root sign. Because of the square root sign, we cannot take the square root of a negative number. So here are the following restrictions, right? This right here has to be positive, right? Otherwise, you are taking the square root of a negative number, and that does not fit in the real number set. So we can write that with this following expression. X squared minus 4 has to be positive. So it has to be greater or equal to 0. Then we would do x squared is greater or equal to 4, right? So that means that x has to be greater than or equal to positive 2, or x has to be less than or equal to negative 2. Okay, because otherwise this will not be a positive number. So since there are restrictions on the x values, this is not continuous. So this is not continuous. Continuous, apologies. And this one rather is continuous. Okay, example 5. Compare and contrast the radical and quadratic parent functions. So this one right here is your quadratic parent function, and this one right here is your radical parent function. So list their common properties and list their differences. So what I'll put right here is I'll do common and what they have that is different about them. Let's start with common. Well, if you take a look at it, they both have the same x-intercepts, right? They intercept the x-axis at 0, 0. So they have the same x-intercept, and they also have the same y-intercept. Same x-intercept, and also the same y-intercept. If we look at intervals of increase, well, this does not have an interval of decrease because it's a one-sided function, but it does have the same interval of increase right here. So this is an interval of increase right here from 0 to positive infinity, and from 0 to positive infinity is also a similar interval of increase. So same interval of increase, which is that this is 0 to positive infinity. Okay, that's your interval of increase. What is different is that this one, however, has an interval of decrease. Interval of decrease for f of x is equal to x squared, right? That is not something that the square root function has. They are both continuous functions along their domain. So the domain for this is from 0 to infinity. It's continuous. And this is also continuous along its entire domain. So they are both continuous along their domain. Both continuous along their domain. Now you might say, well, doesn't this have restrictions right here? It can't be a negative number. That's true, but that is not the domain of the function. The domain of this function is from 0 to positive infinity, and along that domain there are no breaks in the graph. The domain for this function is all of x of real numbers, and there are no restrictions, so therefore both are continuous. Okay, it's continuous. All right. And then they also have the same end behavior as x goes to positive infinity. So as x goes to positive infinity, y both goes to positive infinity. Now what else is different about these? Well, they certainly don't have the same domain, so they have different domains. As I said, in this first example here, the domain is an x element of all real numbers, but in this case, x element of real numbers such that x has to be greater than 0. So they have different domains. All right. The other thing is that x squared, or f of x is equal to x squared. Let's write that. Apologies. F of x is equal to x squared is an even function, because it maps onto itself in the y-axis. Whereas the square root of x, so f of x is equal to the square root of x, is neither. It's neither odd nor even. Okay. One other thing that we haven't talked about yet is the range. So these have different domains, but take a look at the range. That's y is greater or equal to 0. Okay, y is also greater or equal to 0. So they actually, in common, they also have the same range. Okay, so this is a pretty comprehensive list of what these two functions have in common and what makes them different. The final example asks for identify the parent function who has infinite zeros. Okay, so let's think about that. Which of our parent functions crosses the x-axis an infinite number of times? Well, if we think about that, let's draw our x and y axis here. So if it is crossing infinitely, that would mean that it has to be a periodic function. And that means your sine function. Right? As you can see, it continues to cross the x-axis again and again and again. So it has infinite number of zeros. So f at x is equal to sine x. Similarly, you could say f of x is equal to cos x, but remember that the cos x function is just the sine x with a phase shift 90 degrees or pi over 2 radians to the left. State the equation of a function with the range going from 1 all the way to positive infinity. Okay, so that's some information. Is continuous throughout its domain. Right, so there's no breaks in the graph, and is strictly increasing. Okay, well, that's the key there. Strictly increasing, but as you can see here, there are some restrictions on the range. It can only go from 1 to infinity. Well, the graph that I know that is strictly increasing, we talked about it over here. An exponential graph is strictly increasing, right? Okay, so let's draw that out. But if I was to draw that out, an exponential graph, strictly increasing, that is, gets really, really close to 0 and then goes to infinity, right? Continuous, yeah, that's great. But the range doesn't match. So I've got continuity here and strictly increasing, but the range is not, the range is not correct. So what I have to do is I have to take a look at this range. How can I change it? Well, if I shifted this graph up 1 unit, then the asymptote also goes up 1 unit. And so the answer there is f at x is equal to an exponential function plus 1. And that means that it will shift up, and the asymptote, which was at 0, is now at 1, and this seems to work out as well. Okay, just circling back on the original expectations for this lesson. We compared and contrasted properties, and we also sketched functions based on the given properties. Right, so it looks as though we covered all the learning goals for this lesson. Thanks for watching.